Hello, my name is Igor Cadota, and I'm a postdoctoral research scientist at Columbia University. Today, I'm going to talk about our paper, Age of Information in Random Access Networks with Stochastic Arrivals, and this is joint work with Professor Eitan Modiano from MIT in Leeds. Random access networks, and in particular, Wi-Fi networks, they are widely used to support time-sensitive applications such as automated fulfillment warehouses, intelligent transportation systems, collaborative multi-agent systems, and many others. And if you look at those references, you're going to see successful examples of random access networks that are being used to support this kind of time-sensitive applications when the underlying communication network is a small-scale network with a low traffic load. In contrast, if we have an underlying communication network, which is a large-scale network with a high traffic load, then a standard random access network may fall short in terms of performance. In this presentation, we're going to consider random access networks that are tailored for time-sensitive applications. So here you have a random access network with 10 sources generating time-sensitive information and sending that time-sensitive information to the base station. So here you have one of those sources generating packets with a rate lambda and placing those packets in a single packet queue that stores only the freshest packet. So if this source generates a new packet and there's an older packet in the queue, then this older packet gets dropped from the system and the queue stores only the fresh packet. So this is a single packet queue. And if this source would like to transmit a packet to the base station, then it uses random access. In particular, this source is going to wait for a random period of time, and then it's going to start transmitting its packet to the base station. And if this source is the only source in the network to start transmitting at that time, then this transmission is successful. Otherwise, if two or more sources start transmitting at the same time, then there's going to be a packet collision and no packet is going to be received by the base station. So basically, this is going to be a waste of resources and something that would degrade the performance of the random access network. So this is how a random access network works. And in our paper, we analyze and optimize the random access network in terms of information freshness at the destination. And this information freshness is going to be captured by this new performance metric called age of information that we're going to formally define later in the talk. So here we have a few recent works that have considered this problem of analyzing and optimizing information freshness in random access networks. And we are classifying those works in terms of the type of random access network that they considered, in terms of what is the packet generation process in the sources, in terms of whether they consider packet collisions in their analysis and optimization, in terms of whether they optimize the random access mechanism, and also in terms of whether they validate their findings using simulations and implementations. To the best of our knowledge, our work and this paper is the first one to check all those boxes. So we consider both Slotted-ALOHA networks and CSMA networks. We consider both sources that transmit packets on demand and sources that generate packets stochastically. We do take into account collisions in our network model and optimization. We use this analytical model to optimize the random access mechanism, and we verify our findings using both simulation results and implementation in this software-defined radio testbeds that we're going to discuss later in the talk. So this is the outline of our talk. We're going to start by introducing the network model. Then we're going to analyze transmission probability. Then we're going to introduce the concept of age of information and analyze age of information in the random access network. Then we're going to compare the experimental, numerical, and analytical results. So in this presentation, we're going to basically focus on the analysis of the age of information in a symmetric Slotted-ALOHA network. In contrast, in the paper, we go much further. We analyze and optimize information freshness in symmetric Slotted-ALOHA networks, in symmetric CSMA networks, in symmetric CSMA networks with on-demand packet generation at the sources, and on symmetric CSMA networks with low packet generation rates. And if you're interested in those other results, I would like to encourage you to take a look at our paper. So let's start with our network model. So here we have a network with n sources generating packets and placing those packets in a single packet queue and transmitting those packets to the base station using random access. And here we're going to have time, which is divided into mini slots with index k. And now we're going to describe the packet generation process. So at the beginning of every mini slot, each and every one of those sources is going to generate a new packet with probability lambda, and it's going to not generate a packet with probability 1 minus lambda. So source 1 is going to generate a packet with probability lambda 1, and source n is going to generate a new packet with probability lambda n. And those packets are going to be stored in this single packet queue that stores only the freshest packet. Right, so this is how packets are generated and stored in this network. Now I'm going to briefly discuss packet transmission. So here we have the timeline and we have the mini slots. And so in each mini slot K, if there is a transmission opportunity, and we define a transmission opportunity by a mini slot in which at the beginning of this mini slot, there's no ongoing packet transmission, right? So if there is a transmission opportunity in mini slot K, and if there is an undelivered packet in the source, then that source is going to start transmitting a packet with probability mu, and it's going to idle with probability 1 minus mu. So basically, you can see here that this value of mu defines the period of time that you have to wait before starting your transmission. And of course, that if the source does not have a packet in its queue, then it's going to transmit with probability 0. And if in this particular transmission opportunity, only one source starts transmitting, then this packet is going to be successfully delivered to the base station. Otherwise, if 2 or more sources by chance start transmitting the same transmission opportunity, the same mini slot, then there's going to be a simultaneous transmission. In other words, there's going to be a collision and the base station won't be able to receive any of those packets. Here, we're just pointing out that both a packet transmission and a collision, they both take exactly L mini slots. So here we have an illustration in which L equals 3. So in this network model, we have 2 big assumptions. The first one is that all sources, they can detect the transmission from other sources within a mini slot. So here we have a transmission from source 1, and source 1 starts transmitting in this transmission opportunity here, but in the next mini slot, all other sources, they will already have detected that there's an ongoing transmission, and they're going to defer the transmissions until the end of this packet. And this is basically to avoid further collisions. So this is one assumption. The second assumption is that the conditional transmission probability of the sources is going to be fixed. So we're not going to assume that we have any type of binary exponential backoff that would dynamically adapt the value of mu over time. So, and we are assuming that we have a fixed mu because later in the paper, we would like to find the value of mu that would optimize information freshness in the network. And if our goal is to find the optimal conditional transmission probability, then there's no reason to have a mechanism to dynamically adapt the value of mu, right? So that's why we assume that we have a fixed value of mu. Now let's discuss transmission probabilities. So let Qi hat be the probability that source I transmits a packet when there is a transmission opportunity. So here we know already that if there is a transmission opportunity and we know the queue backlog and we know that there is an undelivered packet, then this source here is going to transmit this packet with the probability mu, right? So the transmission probability is going to be mu if there is a packet. If there's no packet, then of course the transmission probability is going to be 0. The transmission probability in that particular transmission opportunity. So basically the transmission probability in a given transmission opportunity is going to be time varying. And it's going to also depend on the history of the packet generation and packet transmissions. So basically, it's going to depend on the queue backlog in that particular transmission opportunity. The problem is that it is challenging to capture analytically this transmission opportunity that is time varying. So in the paper, we're going to approximate this time varying value of Qi hat by its expected time average value, Qi. And next, we're going to have a proposition that gives a closed form solution for this expected time average transmission probability, which we will only call by Qi. So the transmission probability Qi is going to be given by this expression, which is a function of the packet generation rate, the conditional transmission probability, the packet length, and also of this Q of minus I, where Q of minus I is the probability that all sources other than I are idle in that particular transmission opportunity. Right, so this is the definition of Q of minus I. And to obtain this result here, we use in the paper renewal theory and the law of iterated expectations. Now here, I just wanted to point out that the value of Q is always between 0 and mu. This is very easy to see. Another thing that I wanted to point out is that if you change lambda or if you change mu for one particular source, you're going to end up changing the transmission probability of all sources in the entire network. So if you change lambda for one particular source, such as source 1, then you're going to change Q1. But when you change Q1, you're going to actually change Q of minus 2, Q of minus 3, and all other Q of minus J for all other sources in the network, which, because this is changed and this is here, this will change Q of 2 and Q of 3 and Q of all other sources in the network. So the set of values of transmission probabilities actually captures the influence that one source has on other sources in the network. Here we have some important special cases. The first special case is one in which the sources generate fresh packets at every given mini slot. And if you plug in lambda equals 1 here, you get this is 0. So basically the conditional transmission probability is equal to the transmission probability. And this is as expected. Another important case that we're going to go over and over again in this talk is the case of a symmetric Slotted-ALOHA network. So a Slotted-ALOHA network is a network in which the packet length is just 1 mini slot. And a symmetric network is a network in which all of the n sources, they have the same packet generation rate and the same conditional transmission probability. And by plugging this into this value, this expression here, we obtain this expression for the transmission probability. So here we have the transmission probability for the symmetric Slotted-ALOHA network. And notice that Qs, they are just a fixed point of this iterated function. And to obtain those fixed point here, we can just solve the iterative function recursively. So this is how we obtain the transmission probability analytically. So here we're going to consider a symmetric Slotted-ALOHA network with 10 sources, and we're going to plot the transmission probability versus the conditional transmission probability mu. And we're going to consider two types of networks. The first network is a network with a high packet generation rate, and the second network is a network with a low packet generation rate. And we're going to compare the analytical results with the simulation results, which are obtained by simulating the network in MATLAB. So when we compare the simulation with analytical results in a network with a high packet generation rate, we obtain this straight line here, which says that basically Q is very close to mu for every values of mu. On the other hand, when we consider a network with a low packet generation rate, then Q is not necessarily equal to mu in all for all values of mu. And in fact, when we look at the analytical results, we actually get some discontinuities. And characterizing those discontinuities, they are important when we are optimizing the network for the optimal value of mu, when we want to find the optimal value of mu, because later in the paper, we would like to find the value of mu that optimizes information freshness in the network. And of course, that discontinuities in this function, they're going to play a big role in finding those optimal values of mu. So this characterization is something that we address in the paper. Now we're going to introduce the concept of age information, and then we're going to analyze age information in the network. So here we have a very simple system with one source, one single packet queue, and one destination. And I would like to consider this timeline here with the mini slots. So the blue arrows are the times in which packets are generated at the source, and the blue boxes are the packet transmissions to the base station. So the end of the blue box is the mini slot in which the packet gets delivered to the base station. So here we have the number of mini slots between generation and delivery. So this is the packet delay of the first packet. This is the packet delay of the second packet. And this is the number of mini slots between two consecutive packet deliveries. So this is basically the inter-delivery time. And I would like to use those parameters to capture how old is the information from the perspective of the destination. And this is where information freshness is important. So here I'm plotting age of information over mini slots. And I would like us to consider this moment here. This moment is the moment in which the base station or the destination received the first packet, right? So imagine that I'm the destination and I just received this packet. The question now is, how old is the information from my perspective? From my perspective, the information is as old as the information contained in this packet. And the information contained in this packet was generated Z1 minislots ago. So my information is Z1 minislot old. And if 1 minislot goes by and I don't receive anything new, then my information is going to be Z1 plus 1 minislot old, then Z1 plus 2, then Z1 plus 3, and so on, until I receive the next packet. And once I receive the next packet, then my age information is going to be updated to the second packet delay, and then it's going to increase again. So this is the sawtooth pattern that you see in age information papers, and it captures how old is the information from the perspective of the destination. And if you like to keep the information fresh at the destination, you would like this curve to be as close to 0 as possible. However, in this timeline here, we are only considering events associated with source 1 or source I, and in a real network, we're going to have events associated with different sources. But as you can see, the age information only drops when there is the age information associated with source I only drops when there is a packet delivery from source I, right? So it increases and then it decreases only after a packet delivery from source I. But this is the age information associated with only one of the sources. When we consider the entire network, we're going to have n sources generating packets with possibly different rates, placing those packets in a single packet queue, and sending those packets using random access to the base station. And associated with each source, we're going to have a different age of information evolution, right? So next, we would like to capture the age of information of the entire network. And for that, we're going to define this network age information, which is the expected age of information summed over all sources, summed over time, and then we take the average, and we take the limit as the time horizon goes to infinity. So this is the definition of the network age of information, and as you can see, it captures the information freshness in the entire network. So this is the objective function that we're going to consider in our paper, and we're going to try, in the paper, we're going to try to find the value of the mu, of the conditional transmission probability that minimizes the network age of information. But before we can talk about optimization, we need to first find an expression that captures this network age information. And this is our main theorem. The expected network age information is accurately approximated by this expression here. And it's not really important to parse this expression. And I just wanted to point out that in the paper, we use renewal theory, Wald's equality, and we carefully construct auxiliary random variables in order to be able to derive this tight upper bound on the network age information. And next, we're going to use simulation results to show that this approximated expression here is actually accurate. Again, we're going to do a special case of a symmetric Slotted-ALOHA network with n sources. And if we plug in the values of the Slotted-ALOHA network, we get this expression for the network age information and this expression for the transmission probability. And using those two expressions, we can then plot the network age information versus the conditional transmission probability for a network with 10 sources. And again, we're going to compare the results from simulation results and from the analysis that we just did for networks with a high packet generation rate and for networks with a low packet generation rate. And as you can see, the analytical results, they track very well the simulation results. And two things that I wanted to point out is that if we want to find the value of mu that gets you to the lowest possible network age information, then you can see that in this region here, the network age information is flat. So if you have a small error in estimating this value of mu star, then you're not going to incur a high penalty in terms of network age information. However, if you have a big error, or if you're not interested in really finding the optimal value of the conditional transmission probability, as you can see here, you can actually go to regions in which you pay a very high cost in terms of network age information, and this emphasizes the importance of optimizing the network for information freshness. Next, we're going to compare our experimental results with our numerical and analytical results. So here we are implementing a CSMA network with 10 sources. So here we have the 10 sources sending packets to the base station, and each source generates packets with a duration of 50 millislot. And in this network, a millislot has a duration of 9 milliseconds. And we're going to obtain the value of the network age information for different values of lambda and mu. So here we're going to compare the experimental results, which are obtained by measuring the network age information in the software-defined radio testbed. We're going to compare the experimental results with simulations that were obtained by using MATLAB with an analytical results that we obtained in this presentation. So we're going to compare those three things. And here we are considering a network with 10 sources again, in which each source is generating packets with a rate of 0.045 packets per millislot. And here we are plotting the network age information in milliseconds versus the conditional transmission probability mu, and we are comparing the experimental results with the simulation and analytical results. So as you can see, they track each other very well, so we have an accurate model. And next, we're going to show you a video of this operating point here. So this is our network. And here we have the 10 sources generating time-sensitive information and send that information to the base station. And here we're going to plot the age of information over time. So here we're not plotting the network age information, we're actually plotting the age information of the individual sources, and we're plotting them one on top of the other. And here you have the number of packets received by the base station from each one of those 10 sources. So here we have the network age information versus mu. And here's a summary of our work. Again, we started by discussing random access networks that were used to support time-sensitive applications. Then we discuss our network model, and we analyze the transmission probability, and we analyze age information in the network. And then we use a software-defined radio testbed to compare our experimental results with simulation results and analytical results. And we show that our analysis was actually accurate. And again, if you're interested in the optimization of this random access network, I would encourage you to take a look at our paper. So thank you very much for your time and attention.